Hello everyone, welcome back. This is the final video for the open mock paper, and it's probably the last video you're going to see from me until the actual SMO. So we're going to go through the last 5 questions, and these questions are pretty difficult to properly prove, but I'm going to give you more of an intuitive perspective. I'll leave it as a challenge for you to try to write a proper justification, but frankly, for open round 1, where you don't need to give full justification, this is how I would approach many of these questions. Okay, question 21. 3 points are chosen at random on the unit circle. What's the probability that the origin is in the triangle determined by these 3 points? Now, this problem here is actually something that I've known for a while, and there is a pretty standard solution, which is also quite intuitive. However, I realized that this has also been covered on another channel called 3 Blue 1 Brown, which many of you are probably aware of. And he tackles the 3D analog of this, where you're picking points on a sphere. And I think that is pretty interesting, and I would urge you to check it out if you have time. But I'm going to give a solution that is much more straightforward and motivatable in the context of the SMO. Now, the first point, by symmetry, it doesn't matter where it is. So you can just let x be somewhere down there. And then I want to just look at, for each location of y, what's the chance that z would be so-called a good point? Now, if you put y at the same place as x, that's the worst case, because if you put it at the same place or right next to it, your chance is effectively 0. Right? If you put y somewhere down there. Now, let's see if you put y at any arbitrary location, let's say somewhere down here. If you put y down there, then where would z have to be in order to include this point, which is the origin? Well, the furthest it can go would be basically just anywhere within this wedge. So anywhere within this wedge would be just right. In other words, whatever the length of xy is precisely going to be the portion of it in which you're going to be able to have z such that it covers the center. So, therefore, what you need to know is just what's the average portion of the circle which is covered between x and y. And for x to y, it is going to be from 0 to 180 degrees, which is going to be half the circle. If you go somewhere here, be 1/4, let's say, and it's just going to go up from 0 to half. So the average is going to be 1/4. By that intuition, and so the law of 1 over p is 4. Now, if you know some multivariable calculus, or even you know a bit more probability, you can draw a 2D graph and then calculate the area associated with it. I think it's easier to just use this intuition for now, because it just is basically what's the average angle between x and y, and how much of the 360 degrees does that occupy. Okay. Next up is question 22, which looks hilariously messy. What on earth is this? You start off with a very strange sequence. You're then given a very strange function. You're asked to find the minimum value and figure out where that happens, and then you're computing the log of something about it, which is a really weird combination of things to be in the same problem. You have a strange sequence, modulus everywhere, combining into a weird function, minimum value, and a log. When you see questions like these, of course, one thing you can do is skip it, Another thing you can do if you're attempting it is to realize that it's kind of taking you on a journey. So don't panic when you're seeing all of these because they're not really very related to one another. It's just sequential, right? It is some of you have taken a relay round before, meaning that the first guy gets an answer, passes it to the second guy. The second guy uses the answer for his question, gets an answer, passes it to the third guy, and so on until the final answer is obtained. This is that sort of a question. It's just like a miniature relay round within one problem. You have to find out something about the sequence first, so let's start with that. Now, with all of this here and the bunch of fractions, one thing you might be inclined to do, and at least the thing which I hoped you would do, is to divide by an so that it will be a bit nicer. So if you divide by an, what happens is that this is going to be in the form an over an minus 1 squared minus 4 times of an over an minus 1. This is already a little better. I'm going to just let an plus 1 over an be bn. So I'll let it be bn, and bn is now defined by bn minus 1 squared minus 4bn minus 1 plus 6. And of course, bn, the value of b1 is 1.1. Now this doesn't look like it is very convenient if you were to keep on substituting it in, but notice that if we were to complete the square here, you will get bn minus 1 2 squared, bn minus 1 minus 2 squared plus 2. And so it becomes, actually, bn minus 2 equals to bn minus 1 minus 2 squared. Which is nice, because if I were to let Cn to be Bn minus 2, then what you have is simply a successive squaring. Where Cn is, where C1 is negative 0.9. At this juncture, you probably already noticed something. The 0.9 here, it has this mysterious 0.9 that seems to be unrelated to lots of things. Now you see where it comes in. So that is good news. We know that we are on the right track. Okay, so we have found more or less everything we can about the sequence. The question is, what's useful about this information? Well, I'm going to just simply write down all of the information here after C1 because you're just going to keep squaring it. So it means that CK, they're going to be positive after the first term. So it's going to be 0.9 to the power of 2 to the power of k minus 1 because you square it k minus 1 times. I think that is really all we can say about the sequence. We can backtrack it if we want later on, because Bn is just 2 plus this, and that is the ratio. Now, we know that we have just found some information about the ratio, so it stands to reason that for dealing with fx, we can actually factor out the A2s, A3s, A4s, and all of those, so that we will get a ratio on the inside. Now notice that this is telling you the minimum value is going to be determined by all of the sums of these absolute values of x minus the ratio, which is conveniently enough what we want. So what we have found out a lot about. So we found out a lot about the ratio. And if you've done some of these problems before, you know that the absolute value stuff added together, this is just going to be a piecewise function with a lot of straight lines. And the minimum value will occur at one of these ratios. Now, an intelligent guess would probably lead you to say it's probably this one. Because that's the reason for having a log, right? You have a log because there's a lot of powers everywhere. But let's just double check why this happens. Now, we know that CK is going to be this thing which is just rapidly collapsing towards 0. But it's still positive. Now, Bn, or Vk, whatever variable we use, is going to be just 2 plus that. And Bn is the ratio of this. Which means that with the exception of the first two things, right, A1 and A2, it's going to be doubling or more than doubling each time. Right, so it will be something, let's say, more than 44 for the first one. Right, and it's more than doubling each time, meaning that this is going to be much bigger than everything else. In fact, it's so much bigger that if you were to just think about it, this is already the most important value. It's the most important value because if you consider on a number line, you move x away from this, you are going to gain this much. And for the rest of it, you're going to at most lose A2 plus A3 plus A4, and all of that is less than this single one. So I'm just going to claim, and this is quite easy to verify because of what I've verbally explained, this is more than everything else combined. You can look at it as a geometric progression. So this is more than everything else combined. And if it's more than everything else combined, then the minimum value is going to be here at A2021 over A2022. So C is really going to be here. And we can rearrange this a little bit. It means that 1 over C is equal to A2022 over A2021, which is equal to B2021. And 1 minus 2C over C is 1 over C minus 2. So B2021 minus 2 is C2021. So you see where everything comes in. Now C2021 is this, so you're going to log base 0.9. That is gone. And then you log base 32. So your answer becomes just log base 32 of 2 to the power of 2020. And 32 is 2 to the power of 5. So this is equal to 404. So there's sort of a two-in-one question, right? On the left, you have this bunch of sequence transformations, and on the right, we have to try to parse that function. Now, in general, this is how I like to think of these sorts of problems, which is that as you're shifting x, you are shifting it away from that value, then you know how much that term will increase. kind of like a pseudo first derivative test. And for everything else, even if it's decreasing, it is not going to be enough to make up for how fast this one's increasing. In other words, you can say that the point here is a local minimum, which is also going to be the only local minimum among all of these. Okay. Question 23. This is also adapted from a more recent IMO shortlist problem. We are supposed to find the number of permutations of 1 squared to 15 squared such that this product of 1 squared times A1, 2 squared times A2, 3 squared times A3, all the way to 15 squared times A15 is in order. You may have some memories of this from the earlier question where I asked you to sum up all of this stuff, but this is of course completely different from that. I just decided to put squares there almost as a little bit of callback humor. But really the squares are irrelevant. It is no difference from if you just took away all the squares and had it as 1 to 15 here as well as 1 to 15 here, right? Because essentially, if you have a valid permutation, you square root everything and square root these here to get rid of them. It's still a valid permutation. So you can get rid of those and have at least something a bit smaller and nicer to look at. Now, the idea actually is pretty simple if you are not too afraid to experiment a little. So we can think about it this way. Where does the smallest value go? Or maybe you can think of it as where does the largest value go? It's up to you. Now, if let's say that you put in 1 down here, then everything else is kind of left to its own devices. If you put 2 times 1 here, then this one must be 1 times 2. And in a sense, again, everything else is sort of left to its own devices because there's no problem in comparing to 1 times 2 and 2 times 1. If you try to put 3 times 1 down here, you're going to have a problem because then how do you put in the numbers in front of it? Because 2 times 1 is the only thing that can fit. 2 times 2 is already too big. So it doesn't work. And this doesn't just work if you start from 1. This works if you start from anywhere. Like let's say you start from 2 to 15, you have the same logic as well. So this turns out to just be a good old-fashioned Fibonacci recurrence. So if we let let's use f for Fibonacci. Let fn be the number of permutations. For the same problem, for 1 to n, where you adjust the rest of it accordingly. I think you know what I mean. Then it becomes just your Fibonacci sequence. If there's 1 term, it is 1. If there's 2 terms, you have 2 choices. And after that, it just would be fn plus 1. So fn plus 2 equals to fn plus 1 plus fn. So just list out your terms in your Fibonacci sequence up to the 15th one. Here's my laptop does not like the Fibonacci sequence as much as I do. And if you list out to the 15th one, it would be 987. So you have seen perhaps questions like this before, where it turns out the Fibonacci sequence. For example, you would have had those where people are sitting in a row and they rearrange themselves and just take an adjacent seat or the same seat. You have questions where you are supposed to put the numbers in a row, but you cannot have two adjacent of the same. So you have just zeros and ones with no consecutive zeros. You have a question where you want to select some numbers out of a set to form a subset with no two consecutive integers. Now, all of those just have the same idea here, and they all have the same Fibonacci recurrence underlying them. Okay. 24. Decided to have a problem with a bit of local context and contemporary flavor. The Huat family has 14 members, and it's a family tradition they conduct a Yusheng party every Chinese New Year. However, due to COVID restrictions, which were a maximum of 5 people, they conduct multiple parties so that every 2 members attend at least one party together. How many parties do they need to conduct in order for this to happen? Now, the choice of 14 is actually meant to make the bound a bit easier to work with. Why is that the case? Now, think of every one person. Each person needs to have a party with 13 other members of the family. Right, so one person has 13 others to have with, and you know that each party you can at most have 4 others. Of course, when I say at most 4 others, it is quite logical that you would want it to be exactly 5 people, but I mean at most 4 new people because you may have some overlaps in between. Either way, it means that each person needs to attend at least 4 parties. For this to work out. And it means that if 14 members each need to attend at least 4 parties, you need at least 14 times 4, which is 56 slots. And with at least 56 slots and 5 slots per party, you need at least 12 parties. Surprisingly though, this actually is it. It is already a good enough bound. And when I say good enough bound, I mean that you say you need at least 12 parties, but who said that 12 parties is enough so that all of them can have this? It turns out you can, but it is not self-evident that 12 parties are enough. It's just that 12 parties are required at a minimum. Whether it's enough or not, you would still need to try to experiment with how this can be done. How do we do this? There are a few different ways in which you can strategize, but mostly you want it to be as symmetric as possible. So since there are 5 parties, I'm going to just split them into groups of 3, 5 groups of 3 with the exception of the non-existent 15th person who is not here. And we need to find out how to combine them such that they all have parties together. So what I'm going to do as my strategy is that I'm going to go by row first. And then after that, I'm going to go kind of by column. And then after that, I will go diagonally. Now, what do I mean by all of these? Because you can't really say the diagonal because the diagonals only have 3 people and the columns only have 3 people as well. So how do we do this? The row ones are literally those rows. 1, 4, 7, 10, 13. 2, 5, 8, 11, 14, and 3, 6, 9, 12. Now for the column ones, I am going to just adjust it a little bit by, since I want extra space, I'll do something like 1, 2, 3, 4, 5. And then 5, 6, 7, 8, 9. And then 10, 11, 12, 13, 14. Now, at this point, all of those in the same row have had a party together. All of those in the same column have had a party together, with the unfortunate exception of 4 and 6. So I'm just going to use that one extra slot that I have in the rows one to put a 4 in, so that the 4 and 6 would be satisfied. And then I will go diagonally. So what I mean by diagonally, I will go with these so-called toroidal diagonals looping around. So these will be my 3 groups, which is 1, 5, 9, 10, 14. There's a lot of repetition in who has parties together, which is not surprising because if they attend 4 parties, they will be with 16 other people when they only need 13. So overlaps are quite okay here. So 2, 6, 7, 11. And 3, 4, 8, 12, 13. And then I will go in the opposite direction for the same thing on the other end. So something like this. Need to make sure I'm using different colors, otherwise can't really distinguish them. Okay, so something like that. Now, this is not the only construction, but it is one of the ways in which many of these kinds of grouping things are constructed. So 1, 6, 8, 10, 2, 4, 9, 11, 13. And 3, 5, 7, 12, 14. Now, of course, a question you might ask is, how do we know we haven't missed anything? Well, same row has been covered. Same column has been covered. And diagonally, every 2 that are in different rows will either be in the same diagonal in the so-called upward direction or in the same diagonal in the downward direction. So you know that everything would have been covered just right. Okay, last one, question 25. This is a relatively tricky geometry question, but if you make a couple of observations, it doesn't require that much angle chasing non-stop. So in triangle ABC, let's draw a triangle. I highly doubt I'm going to get the 27 and 41 degrees to look remotely accurate, but I will try. So I'll do ABC. D is just any point on BC. I'll hold that off for a moment. EF are the feet of the perpendiculars from B to AC. And C to AB respectively. Okay, so let's draw in those perpendicular lines with a different color. Now, BE and CF intersect at H. H is the orthocenter. Orthocenter is because every triangle, all 3 perpendiculars are supposed to intersect. So we don't know whether we will want to draw a H in, but we might. We'll see. While the circumcircles of BDF and CD, okay, so here's where we definitely need the point D. BDF and CDE, their circumcircles intersect at point P. Let's say D is somewhere here. Sorry about this, it happens every now and then. So you have one circle there and another circle at the other side. The intersection is supposed to be at point P. Okay. And now we're given a couple of angles, EFH and BCA. Okay, so I need to highlight that point. I will highlight it in a bright color so that we can see. It looks like it's going over that point H. H is here, so I will just label H. This is H, this is P. PFH is 27 and BCA is 41. Find angle BHP in degrees. I don't really want to label those angles yet. I want to look at this diagram and just stare for a moment. So what can we say? The first thing that we can actually say is that we have got this pair of right angles down here. And so we have a cyclic quadrilateral AEFH are concyclic. But also, if we were to look carefully at the rest of the figure, it kind of looks like P also belongs to the same circle, right? And that turns out to be true because P is something that we call the Mikkel point. Now, the Mikkel point, we don't actually need to know this, but I just want to give it a name so it's more memorable, that's what it's called, is that when you have two circles drawn in a triangle, like let's say BDF and CDE, and they intersect at P, it means that A, F, E, and P would also be concyclic. Now, the reason for that is actually pretty simple. Let me write this down first. A, F, E, and P are also concyclic. The reason can be explained using just any other triangle really. So I'll just draw a triangle below and say something like this. Right, let's say that if this is concyclic and this is concyclic, it means that these opposite angles sum to 180 degrees. And these opposite angles also sum to 180 degrees. So that means that the other two opposite angles must also sum to 180 degrees. Because then you would get a total of 540, which is from the triangle and the angle at the center. So you get these must also sum to 180 degrees. And this is no matter where the points are located. As long as you have two cyclic quadrilaterals, the third one is also cyclic. So in that case here is AFEP that is going to be concyclic. Now AFEP and AFEH are both concyclic. That means that they're on the same circle. So I can actually draw a third circle passing through all 5 of these points. And now we have got plenty of choices for how we want to finish. I'll just remark, same circle. Because they share 3 common points, so it must be the same circle. Now, how do we get to angle BHP? As I said, there are a few different options for how one might want to go about this. You can perhaps most easily just look at this point H and find all the other angles around it. If we wanted angle AHP, we can do that because angle APH is also going to be 90 degrees. So AHP is 90 minus HAP, which is 90 minus 27. We also have angle AHB. And remember that in this configuration, H is the orthocenter. H is the orthocenter means that if you extend this down, this will also be right angle. And so AHB would just be equal to, let's just call this point D prime. AHB equals to angle EHD prime. And in any orthocenter configuration, you always get bunch of cyclic quadrilateral. So here, angle EHD prime is just 180 minus ECD prime, which is 180 minus 41. So we have got these two, and what's angle BHP? BHP is just 360 minus these two, right? That's the reason why we chose to find those two angles after all. So 360 minus those two angles, those two add up to 202. So that is 158 degrees. Right, and we're done. Now, this last few questions, of course, took a while because we are covering quite a lot of ground just within each problem. But that's to be expected when you're on the last few questions of the SMO Open. Having said that, that does not mean every question takes a long time, because as we saw for something like question 21, once you get the intuition by just playing around with where the second point goes, it just takes you a minute or two. So don't wholesale skip all the questions behind, even though you might expect some of them to be really tricky. All right, so I hope you found this useful, fun, and also somewhat instructive. Feel free to leave any comments below. And if you're watching this before the SMO takes place, all the best for that. Thanks for watching, and see you again soon.